after a collision, it will always travel faster than the pool ball, even if I throw the pool ball at the racquetball. Here you'll notice it does move faster because it does have less mass. Now if I tape the two of them together and again hit the racquetball with another pool ball, you'll see it curves around the pool ball. In this final demonstration, I hit the two pool balls, and because the racquetball has not been hit, it just goes along for the ride.
This ball and cup was one of the more difficult toys I've demonstrated on the flight. You can see that the ball just won't stay in the cup as it does on Earth. Of course, on Earth we have gravity holding the ball in the cup, but in this microgravity environment, when I put the ball in the cup and then push to hold it, I've actually pushed the ball away. So I never could get the ball to stay inside the cup. We'll try again. You can see I just push on the ball and that pushes the ball out.
In this scene, I try to throw this ping pong ball the old-fashioned way, but it doesn't curve down toward the target like I would expect on Earth. So I have to change my throwing style. I throw it straight at the target without any twist at all, and then I attempt to throw another ball with some twist to see if it changes the direction of the ball as it goes to the target. Let me try this again. Straight with no spin. Oops. Now one thing you'll have to remember is that the Velcro of the ball does have to touch the target. Let me try this again. There we go. And then I'll throw it one more time with some spin to see if the trajectory toward the target curves. Looks to me like it did a little bit. Now in this scene, I take the target off of the lockers so that it's free floating, and this is a good demonstration of how one object will react when you hit it with another object in space. Now it's floating around, in part because of the way that the first ball hit it, so I'll throw another ball to try to change the direction of the floating. I got it to work. Horseshoes isn't played the same way in space as it is on Earth. Here I try to throw a shoe the old-fashioned way, and as you can see that without the effect of gravity, the shoe just bounces off. I try it one more time, just to demonstrate the point, and then I decide I'm going to change my technique. Instead of throwing the shoe right at the pole, I'm going to use a spinning motion to see if I can catch the pole. And in fact, that's exactly what happens. At this point, the shoe is pretty stable in a spinning motion around the pole, and in fact, this ended up spinning for a total of about 5 minutes. Without the effect of gravity, it doesn't slow down and settle at the bottom of the pole. In this demonstration, I take the horseshoe pole off of the locker and let it free float while I throw the shoes at it. That didn't work too well. In this demonstration, I decide I'm going to throw a horseshoe at the pole in 3 different places to see how the pole reacts. In the first demonstration, I throw it as low as I can to the base. And as you can see, there isn't much spinning motion of the pole itself as it reacts from having the shoe thrown against it. I'm going to try a different technique. How about the middle? Okay, I begin to see the pole turn as it reacts to the shoe being thrown at it, and it floats away. One last try by throwing this horseshoe at the tip of the pole to see if I can get it to turn even more as it free floats away from me. Certainly seems to.
Basketball is a sport that's near and dear to my heart here on Earth, and I was very interested in seeing how basketball would be different in space. As you can see, I start out with a standard free throw type shot, and the ball just caroms off in a funny direction, not anywhere close to what you would expect from shooting the same shot here on Earth. So I keep changing the angle from which I'm shooting, and I'm finding that it is pretty darn tough to make a shot in space. Finally, I look at it and I think that the only way to get the ball in the hoop is either to come up real close and slam it through, or to try to bounce it off the ceiling. That's the only angle that seems to work. And note that the ball stops in the basket. It doesn't get pulled all the way through. The next thing we tried was attaching the hoop to a free-floating book. You can see that every time I hit the book, which is now the backboard, with the very lightweight basketball, I can actually make the book and the hoop start spinning. Well, that makes life difficult when you're trying to make a basket up there, and I ended up coming up with a very simple approach. Just hold the book steady. Otherwise, it becomes very difficult to make a shot with a free-floating basket and backboard. One of the things that's always impressed me here on Earth was the ability of the professional basketball players to spin around and make these really neat moves. Well, I was trying some of that in space. You can see it's pretty difficult. It's hard to control your body up there. I finally managed, after a while, after a number of tries, to figure out a way to go head over heels and accomplish a slam dunk. This is my entry into the NBA Slam Dunk Contest for next year.
Now I know on Earth you think this toy works very well, but in space we couldn't get it to work at all. We had this thing floating around, but without the effect of gravity it just doesn't work the same way. Now I took this toy, looked at it for a number of minutes, and tried to figure out what in the world do I do with this thing up here. It took me a while to finally come up with something that appeared to be unique in space about this toy. Watch when I close and open up the Jacob's ladder. Every time I did this, the ladder would turn into a different configuration. It was completely random, and we, the astronauts, couldn't ever really predict what would happen when we pulled apart Jacob's ladder. To this day, it still seems a mystery.
Here I am trying to produce standing compressional waves by holding one end still and moving the other end in and out. The result had some transverse motion to it because my hand also had some up and down motion. In the next sequence, I tried to produce compressional waves by moving my hand in and out a bit faster. Then I tried to produce the same type of wave by moving both ends. Next, I tried to stretch the wave out. And then I transitioned to producing transverse waves, first slowly, and then with a higher frequency and amplitude.
These magnetic rings are really interesting. I've got them arranged on this plastic rod so that the poles of the magnets are opposite to each other and they repel or push away. And you can see when I release the rings, they spring out equally along the plastic rod. And it doesn't matter whether I hold the rod up or whether I hold it down, because in this microgravity environment there is no up and down. They spread out equally along the plastic rod and push away from each other. Now I'm going to rotate the plastic rod very slowly. We'll see what happens. The rod is rotating so slowly that the magnetic force still keeps the rings pushed away from each other, and the spacing is about equal, about what it was before. Now I'll rotate the rod faster. Now see what happens. Now the rotational force has overcome the magnetic force and the rings are pushed together.
The magnetic marbles were a lot of fun to play with. What we were looking at initially was how far apart can we hold two marbles and have them still be attracted to each other. The first time we did it, we had the opposite poles facing each other so they would be most attracting. The second time we tried about the same distance apart, only with the like pole facing each other. Sure enough, they attracted there as well. This time, the marbles were just a little bit too far apart and they didn't attract. I put them closer together, but I started the one on the right in your screen with a little bit of motion. And that motion was just enough to overcome the attractive force, so they did not come together. Now I'm looking at the influence of one marble on the other without touching it, seeing how close I can come with one marble and how much I can make the second marble, which is free-floating, spin as a result. You can see that every time I make a pass around the marble, I'm affecting the spin of the marble, and actually I'm even pulling it towards the marble in my hand. Now I'm looking at releasing one marble with two marbles attached together to see if there's any difference in the attraction. It looks like the two marbles are pretty happy being by themselves and that third marble is left out. This time I'm putting the third marble in motion, and sure enough, if it gets close enough, it is attracted by the other two. Now I have strings of 4 marbles each, and we're going to see if they come together. That's a funny looking snake-like thing. We got a big kick out of seeing that. And then you tap it in the middle and it turns into a ring. This time I have 2 sets of 4 marbles and they had the like pole facing each other, so they were repelling each other. And they would swing back and forth and they actually did repel each other. And they're pushing each other away. Now I've got one set of 5 marbles, one big one in the middle and 2 little ones on either side, and I'm seeing what influence I can have on those 5 with one small marble. And look, it attaches to the end of the string. This time I start with the blue face of the small marble and the 5 marbles together facing each other. Initially they repelled, but eventually the attractive force overcame it and they came together. The next thing we took a look at was a string of marbles. We wanted to see how they reacted when we spun them around. As I spin them, it becomes more and more difficult as I go faster and faster for the marbles to stay together. Where do you think they're going to let go? Now I have 2 rings of magnetic marbles. I pass them very close to each other and they show no sign of attracting. They seem to be very happy just being on their own little ring. But if they get close enough and they're moving slowly enough, they will attract. Now let's try it with them very close together, moving very slowly. You can see they just are very happy to be on their own, and there is not nearly as much attractive force as there was earlier with the 2 individual marbles.
The comeback can wasn't quite as interesting on orbit as it is here on the ground. I could let it go here as I spun it up, and you can see how its rotation rate increases and decreases as the metal weight catches up. I also tried to spin it up before I let it go, and you can see it rotates quickly one direction and slightly goes the other direction, back and forth until it comes to a stop. But because you can't lay it on a table and spin it up and have it roll down the table or come back to you as you let it go, it's not as interesting here.
In this first sequence with the car and track, I had wound the car up and just let it go without the track. And here, because of action-reaction, you see the car doing an end-over-end wheelie. Next, I tried to get the car to run on the wall. The main result when I release it is that the car springs back toward me off the wall from the little force I had applied with my hand to hold it there. Getting the car to run on the track was a bit easier in space than on Earth because the car didn't have to build up as much velocity to stay on the track as it did on Earth. In the second sequence, I got the car started and then let it go. Here you see that second sequence in slow motion. Wherever the car is on the track, the whole system, car and track together, moves toward that general direction. Next, I started the car on the track by giving it a push rather than winding it up. In this case, we wanted to see how long the car would stay on the track if I held the track steady enough where I wouldn't bounce the car off the track. Even though I knew intuitively, by the laws of physics, that this would be the case, it was amazing to me that any forward velocity of the car at all was enough to provide the necessary centripetal acceleration to keep the car on the track. Here in this second sequence, where I just push the car rather than winding it up, in this view the car ends up stopping on the top of the track. This was amazing even in space to see the car creep along ever so slowly and then stop and sit there at the top. Finally, the car comes off the track and winds up in the center of the track before they both slowly drift away. Next, in a demonstration of centripetal acceleration, I get the car started on the track and then open the track. Once there is an opening, the car flies out in a straight line.
Okay, I'd just like to remind all the folks that are watching out there that, especially the children, that science applies to everything, even toys. And we hope that our demonstrations today have given you just a taste of scientific research in space. And we want to encourage all the children out there to do well in science and math, and to learn all you can about the world around you, because we need people like you to design and maybe even fly the experiments of the future. So as we say goodbye, we're going to release all of our toys at once. 1, 2, 3, now. Okay, bye-bye everybody.